Good morning. On Friday, I promised you that today is going to be a really boring lecture. Well, I lied. It's going to be a regular fun physics class. These handouts replace your Friday's handouts. I just added a couple of slides, so you can keep your old slides for lecture. And here we have the set of problems. Some of these problems we're going to do together. Some of those problems you can just work out at home. So these four pictures represent all cases related to application of Lenz's law when we are looking for the direction of the induced magnetic field or induced current. It's a straightforward problem. We know what is happening to the external magnetic field, and we can figure out what is happening to the induced magnetic field because it always opposes the changes happening to the external magnetic field. And another situation is when we know the direction of the induced magnetic field and looking for situations when it might happen. And in this situation, in this case, well, we might have several possible answers. Two, more exact. So if the induced magnetic field is given, well, in that example, it points up. How can it happen? Well, first situation is when the external magnetic field points in opposite direction, but increases in magnitude. So the induced magnetic field is supposed to compensate that change. Another case when the external magnetic field has the same direction but decreases in magnitude. So the induced magnetic field supports the external field, opposing the change, supporting the field. And that basically completes all theory related to Lenz's law. Well, we may ask the question, how else can we change the flux through the loop? Instead of just changing the magnetic field, what else could be done? Well, the flux is a product of three variables: field, area, and, well, cosine of the angle. So if we change any of these variables, we can change the flux. If we change two variables at a time, in that case, two changes might compensate each other. So we have to be careful when two variables change. However, if only one variable changes, only B or A or theta, flux changes. And in that situation, changing flux generates induced magnetic field, induced current. And it doesn't matter what is the actual reason for change. Magnetic field changes, area changes, angle changes. As long as the flux changes, there is a current. And we know that the current is related to EMF and the resistance of the circuit. That's just Ohm's law, not a new law. So when flux changes, we have to conclude it generates EMF in the loop. And the law which relates EMF generated by the change in magnetic field is really simple. Faraday had it found. Well, for one loop, n equals 1, if we have a coil, we just have to multiply EMF generated in each loop by the number of loops. And this is the only new equation we'll learn today. We just have to look at different examples of how to apply this equation. When we're calculating magnitude of the induced EMF, magnitude of the induced current, this minus doesn't matter. It's much easier just using absolute values. Minus is related to this word, to oppose. The induced magnetic field opposes the changes, and mathematically we have to reflect it in this, well, sign. We have to remember that when we use a specific measuring device, we have to assign a positive direction for the current, or we can say we have to assign a positive direction for area vector. In all our examples here, so far, this is our measuring device. Positive direction of area vector is out of the screen. Positive direction of induced current is counterclockwise. So if we have induced current clockwise, it's negative, and deflection points to the left. Negative and positive related to this expression. Again, if EMF is negative, current is negative. If EMF is positive, current is positive. Resistance is never negative. So this calculation also gives us the way to figure out the direction of the current. If we keep our agreement, a negative value for EMF gives negative value for current, a negative value for current says it's clockwise. A positive value for EMF gives positive value for current, positive value for current says it's counterclockwise. Actually, yeah. Let's just see how it works in this example. So we did this experiment actually several times. And when the magnet initially is far away, we have a small flux value, but it actually is also a negative value, because according to our agreement, when the area vector points out of the screen and magnetic field points into the screen, the flux is negative. So we can assign, like let's say, -2 Weber, the initial value of the flux. When the magnet is getting closer, well, the flux remains being negative, however the magnitude increases, so we can assign, let's say, well, -10 Weber. So now we can apply the Faraday's law. It says EMF is supposed to be equal to minus delta phi over delta t. So one loop times one. So in our situation, that would be equal to minus. What does delta mean? It means final minus initial. So it means -10, -2. Delta t is always positive, and time doesn't go back. So what number do we get here? Well, 8 over delta t is a positive number. So this choice of the area vector gives a positive current, counterclockwise current. If we just apply the Faraday's law directly. And now we just have to solve more and more problems related to Faraday's law. This is one of these problems. So I'm going to give you a minute. You can calculate the value of the current and choose one of these answers. Actually, I'm going to give you maybe a little bit more time. Sheet already on the sheet? Do you know?
equation sheet.
So that's 2.
The equation sheet is alongside the Hampton assignment. This is Hampton assignment equation sheet.
Thank you. I suppose all these equations are supposed to be on the equation sheet, so you don't have to memorize those equations. I don't know the answer, so I have to solve it the way you did it. I have to throw an answer somewhere.
Well, so what do we know? The area, the resistance, magnetic field, and the delta t, the time interval, and initial value for the field and final value for the field. So, and just one loop. EMF is supposed to be equal to minus over 10 seconds. Final value. Well, 0 times anything is 0, so it's 0 minus the initial value of the flux. It's supposed to be equal to the area, which is equal to what? 0.5 times magnetic field, which is 1. What is the value of this angle? I said, I heard someone said 90. What do you think? Okay, that's better. Now we have two choices, 90 or 0. If we have this angle equals 90, cosine of 90 equals what? 0. So we would have to make 0 minus 0, it would be 0. We wouldn't, we don't have a choice like that. So probably it's not 90, and it's not, because we have to measure these angles between the field and normal to the loop. So this is the loop, the normal, which is perpendicular to the loop, is down, well, into the screen, and the field is into the screen. So there is no angle between these two arrows. It's 0, cosine of 0 is 1, so times 1. So this is EMF, and that gives us 0.05 volts. And we have to divide it by EMF over R equals 0.005 over 0.5 amps. That's supposed to be the answer number 2. Well, of course, we get much clearer calculations here. The answer is 0.5. And instead of decreasing magnetic field, we can have increasing magnetic field. It doesn't change the way we think through the problem. Or here, in this situation, we change the time. Instead of 10 seconds, all it happens in 2 seconds only. So what does it do? It increases the EMF 5-fold, so it increases the current. We're not going to do this problem. Exactly the same calculation, but magnetic field increases, so final value of the flux is larger than the initial value. This is also a possible example when we have two sources. 2 wires are involved. Number 1, number 2. So in this situation, the induced magnetic field equals the sum of individual induced magnetic fields. Let's say this current doesn't change, constant. But this current increases in magnitude. what would be the direction of the induced magnetic field in the loop? Well, we know what to do. Yeah? If this current doesn't change, that means magnetic field number 2 doesn't change, constant. That means the flux, which is not 0, number 2, but more importantly, it's not 0, but the change of the flux number 2 equals 0. It doesn't change. That means this wire, number 2, doesn't induce any EMF. Only wire number 1 induces. And we can figure out the direction of external magnetic field generated by wire number 1 is into the screen. Magnitude goes up. The induced magnetic field is supposed to oppose that change, which means in this situation it's also supposed to oppose the external magnetic field. That's the induced magnetic field. Let's say both wires have changing current. Well, in that case, we have to also figure out the direction of the magnetic field generated by the second wire, see what's happening to it, and figure out the direction of the second induced field. They might have opposite directions or same. If they have opposite directions, which would win? Faster change leads to higher EMF and to stronger induced magnetic field. Well, how else can change be happening? Another situation like that. Two loops travel in the magnetic field generated by a wire, but they travel in different directions. So change happens differently inside each loop. Well, which change happens faster? We know that when the loop is traveling parallel to the wire, there is no change. We had a question like that, which means if we have any general vector of velocity, arbitrary direction, we can resolve it in two components. The parallel component of velocity doesn't do anything. Only perpendicular component of velocity is important. So whichever loop has a larger perpendicular component of velocity has higher induced EMF in it because change happening faster. Well, this is just supporting calculations. One more way to compare induced EMFs. Now, two loops, they have the same velocity. However, now they placed differently. One is closer to the magnetic, to the wire-generated magnetic field. Another is farther away. Well, first of all, of course, the magnetic field is different. If we're close to the wire, magnetic field is strong. If we're far away, it's weaker. But magnitude of the magnetic field is not important when we talk about change. When we talk about change, the rate of change is important. But on a graph, the rate of change always is represented by the slope. And if we look at these two loops, at these two locations, here the slope is also larger. So change is happening faster here. And that means the induced EMF in the loop number 1 is higher. And here we have a supporting algebraic calculation. Basically what we say is the magnitude of induced EMF is related to the slope of the graph of magnetic field as a function of distance. Larger slope, faster change. Well, of course, as long as loops travel with the same speed. Well, it's very important to read the graphs correctly. There are many problems related to graphical representation of change. What kind of change? Again, magnetic field or current. So this is the first example. The magnetic field changes like that. So what kind of change is it? Increase. It goes from 0 to 0.2 in 4 seconds. Now we know everything to apply the Faraday's law. The Faraday's law is this. So to calculate the final value of the flux, well, the initial value of the flux is 0. To calculate the final value of the flux, we have to calculate this for one loop and multiply by the number of turns. That gives 0.3. And now we just have to apply the Faraday's law. What does this mean? Well, we know this is supposed to be related to the direction of the induced current. And so far, we always use that specific loop and that specific agreement and that specific multimeter for which area vector out of the screen related to positive counterclockwise current. So minus means this current actually is supposed to be clockwise, and this multimeter actually is supposed to be flip arm to the left. If we want to draw a graph for current as a function of time, what would we do? Well, if EMF is constant, we would have to divide this value. Well, current equals negative 7.5 over R. R is supposed to be the total resistance of the coil. And that's, again, supposed to be some negative number. So for this graph, to represent the current as a function of time, we would have to draw a line like that. It's a constant current, but it's negative. And now, I'm going to give you a minute just to practice. Oops. I gave it up. No, I didn't. What you need to do is you need to sketch a graph for the induced current as a function of time. It's a very common exercise and it's a very common question. The graph for the flux is given. All the equations you need are given. So all you have to do is just make a sketch for the graph of the induced current as a function of time. In a way we just did a minute ago, but a minute ago our graph was shorter. A minute ago our graph looked like that, right? So we will already know the answer for this part. But this graph has two more parts. So your graph for the current also should have two more parts, three totally. What I usually recommend is, well, it's not a serious question, so I can talk. What I usually recommend is actually placing the axis right below the given graph. It's easier to deal with graphical representation. So, first of all, if you look at the Ohm's law, the graph for the current, just squeeze copy of the graph for EMF. Well, maybe stretch copy, depending on how However, what we know is that this variable R doesn't change the shape of the graph. And we just multiply and divide it by some positive number. So if your EMF looks like this, your current should look in the same way. If your EMF looks like this, your current should look like that. So basically, the question is, how would the graph for EMF look like? And to answer that question, we have to look at this law, Faraday's law. First of all, it's related to the change of the flux over time. Its slope. So how does this slope of the flux look like? This slope. Is it zero, positive, or negative? Positive and constant. This slope, zero, positive, or negative? Negative and constant. It's hard to say, but I think this line in the elixir actually goes faster down, so magnitude is probably larger. And finally, this part, the slope is zero, positive, or negative? Zero. So this is how the graph for the slope of the flux as a function of time looks like. All we have to do, we have to flip it over because EMF equals minus this. So positive becomes negative, negative becomes positive, zero remains zero. This is graph for EMF. And for the current, the graph would look exactly like that. Well, if we had actual values, we actually could calculate the values for EMF and for the current. This is my question to you. Now we have 3 graphs. And if you look at these graphs, you can figure out EMF at any time for any graph. But so far the question is, at t equals 3 seconds, which of these graphs gives the current of the largest magnitude? Perfect. That's exactly what you think about it. Thank you very much. You're both right. So let's still have to wait 8 seconds to change your answer. And if the number of responses doesn't change anymore, so that means that you just and why do I never get 100% correct answer? Well, okay. I'm back. It is not a tricky question. You just look at the slope at that particular instant. Well, 3 seconds, it's here between 0 and 5. There is no change, no slope, no EMF, no current for case A and for case B. So EMF is 0, EMF is 0, so does current, and only case C represents a case with a current at t equals 3. So it is the largest one. And of course, we can pick any additional graph, any additional time, and ask anything about currents and fluxes. For example, here, another question to you. At t t equals 8, for case K, what do you think is the direction of the induced current? Again, we stick to our general assumption. So you pressed the button finally. What was your answer? Clockwise, why do you think so? Exactly. So when, what do you mean positive? Flux or change? Change. So we have to look at what is happening to the graph. If it goes up and at t equals 8, it does. Yep. So 8 seconds is here. This is the actual value of the flux. Well, let's say point something. Yeah. It's not 0.1. It's positive, but it doesn't matter. It would be a negative value. So at t equals 8 or at t equals 6, when the flux is negative, the change is the same. So between 5 and 10, the slope is positive. When the slope is positive, EMF is negative and current is negative. And for the negative current, it's supposed to be counterclockwise, which means clockwise. Now we can actually calculate a specific value of the current. So please, again, take a minute. Just read carefully. This is now not a loop, it's a coil. It has 30 loops, 30 turns. Its resistance is 20 ohms. All right. Since you need to write something, calculate something, I'm going to add something. You see? It's not boring at all. The only tricky part in this problem is calculating delta phi over delta t, calculating the slope. And let's do it. So, well, the slope is the same everywhere between 5 and 10. T equals 8 is here. So I wouldn't use t equals 8 for calculating the slope. I would use this point, right? because I know the value for the flux is 0.2. So all I do to calculate delta phi over delta t is going to be 0.2 its value divided by, well, it's 10 seconds, 10, 0.02. You don't agree? Why? Some people do that, believe me. But that is wrong. So please, don't do it this way. If you want to calculate the slope, we have to compare 2 points which belong to the same part of the graph. This one. So delta t equals 5 seconds here, and delta phi going to be equal to what? 0.2 minus negative 0.2, 0.4. Now, delta phi over delta t is 0.4 over 5. And we have to multiply by the number of turns, which is 30. And we have to divide by the resistance, which is what? 20. Well, we are looking for the magnitude, so minus doesn't matter. We just use absolute values. Well, this is a clearer writing for this particular calculation, and the answer is 0.12 volts. Any questions at this point? Because we are almost done. Well, of course, there are many other situations similar to a problem like that. Many possible graphs could be given to you. What we're going to talk about is this. Okay. Apparently, I don't have it. So what is happening? There is a loop which is traveling at constant velocity. And when it's traveling through two regions with magnetic field, what is happening to it? That's what we have to figure out. Well, again, first of all, we have to assign a positive direction for area vector. Without that, we cannot say which flux will be positive, which flux will be negative. And in this situation, we assume the positive direction is into the screen. So it contradicts our general agreement. So into the screen, what is happening? When the loop is completely outside of the magnetic field, there is no flux at all. Only when the loop is entering the field, we're getting some flux through the loop. Plus, the more of the loop is into the field, the more area, the more flux. The flux goes up for a while. Then the loop is completely inside this region. And the flux doesn't change anymore. So it remains constant. Then the loop is entering another region. In that region, magnetic field changes its direction. So which means positive flux decreases and negative flux increases. So it doubles the speed of the change which is happening to the flux. And eventually this loop again is into the second region completely, and the flux doesn't change anymore. And finally this loop leaves the magnetic field, the flux gradually goes to 0. And now, as long as we know what is happening to the flux, we can immediately figure out what is happening to the induced EMF and induced current. 0 slope, no EMF. Positive slope, negative EMF. Zero slope, no EMF. Negative slope, positive EMF. And you see, it's twice larger in magnitude. And again, zero slope, no EMF. Positive slope, negative EMF. That's it. Well, now we can make a different conclusion, more general conclusion. It doesn't have to be a straight line for the flux to figure out what's happening to the magnetic field and what's happening to the induced EMF and what's happening to induced current. Any kind of graph has only two options for the slope. It's either positive or negative. So if your graph has this kind of a part or this kind of a part, the slope is positive. If your graph has this kind of a part or this kind of a part, the slope is negative. For the positive slope, we have negative current and negative EMF. For the negative slope, we have positive current, positive EMF. And this is a setup very similar to you're going to be using in the lab soon. Faraday's law lab. Here what you have is a magnet. Magnet falling down through this pipe. Well, what's important is that this magnet goes inside this coil. Well, you may have different coils. This coil has 800 turns. Your coil might have 400, 600, 1600. It doesn't really matter. So we know that generally the red end represents North Pole. So close to this pole, magnetic field lines point straight down like this or up like that, depending on orientation. So here, when the magnet is falling through the coil, the flux changes over time. Well, how? It depends on the choice of area vector. Well, you can use some interface. In your situation, at least if you go on Monday, the setup will be ready for you. Then you might have to reconnect some of the wires. And here. So this interface, computer interface, replaces the multimeter, the galvanometer. So it actually plots the function for the flux and the EMF induced in the coil as a function of time. Well, normally if you read the manual, that will tell you that magnetic field pointing down should represent positive flux. So magnetic field lines passing the loop down should give you a positive flux. What loop is not a positive flux, it's a negative flux. So what do we do? How can we make it positive to bring in agreement with the manual? What can we do? Anyone please say any suggestion? I'm going to move on. Yes. Well, if we flip the magnet, it changes the orientation. The manual says, for the magnet with North Pole down, flux must be positive. So we have to keep the magnet with the North Pole down, and we have to make this flux positive. Exactly. That's all we have to do. It's all about connection. When we switch the wire, basically, we change the orientation of the area vector. We could switch the whole coil, but basically that's the same thing. And now, for the North Pole pointing down, the flux is positive. That's the flux. That's the voltage. You see? Positive slope gives you negative voltage, and the negative slope gives you positive voltage. How do we get these peaks? Well, if you look at the picture, if you look at the picture, that's what is happening. The slope curve increases, then the slope decreases. So there is a point where the slope reaches its maximum value at this point. And over there, the slope decreases and increases. Again, there is a slope where it reaches its maximum value over here. So we can apply the Faraday's law to different situations. Two other very common situations. When the flux changes like this, it looks like a simple harmonic motion graph. But if the flux changes like this or like that, all we have to do to figure out what's happening to the induced current or EMF is just analyze what's happening to the slope. The slope is zero. When the slope is zero, there is no current. The slope is positive, negative current. The slope is negative, positive current. Slope decreases, current decreases in magnitude. Slope increases, current increases in magnitude. Well, this is an example of a problem like that. There is a graph for the change in flux, and you have to compare currents and induced EMFs at different distances. So what do? You just look at the slope. The slope of this tangential line, well, at point 4, for example, the slope is 0. That means there's no induced current. If you want to compare the induced current at point 2 and at point 3, which would be higher? Well, this one gives larger slope, higher current. Any questions? This is how the Faraday's law works. My last question, we still have actually 3 minutes. So, let's say we run an experiment like that. But in our experiment, let's say if we read the problem, it says positive flux or field directed up. So for this magnet, the flux is negative. So this is the graph for the flux. Okay? My question is, which of these 4 graphs represent the graph for induced EMF or current? 1, 2, 3, or 4? And, oh, 37. We got one more student. Okay. Well, again, let's see, answer 3 is correct answer. Thank you very much. All we have to do is look at the slope. Here, the slope is negative, so it should give you a positive EMF. This one, this part is positive, and it should give you 2 peaks, so this graph doesn't work. Any questions? Well, thank you very much.